The cosmos began in absolute darkness. Long before our sun or moon even existed, the very first lights in the universe flickered on. We are about to become cosmic detectives, uncovering 30 profound mysteries surrounding the birth of the first stars and galaxies. By the end of this journey, you will hold the pieces to the greatest origin story of all. How did a single star ignite in a void of pure hydrogen? What cataclysmic explosions forged the very elements that make up our world? What forgotten truth are we on the verge of discovering? What does it feel like to trace our own existence back to the very beginning of everything? Our cosmic origin story begins with a star that was nothing like our own sun. These first stars are classified as population 3, and their nature is our first great mystery. They were not just larger, they were titans, behemoths that could have been hundreds of times more massive than the star that warms our planet. This immense size came from a simple, pure composition. The universe was too young to have forged any elements heavier than hydrogen and helium. There was no carbon, no oxygen, no iron. These first stars were built from the universe's primordial ingredients alone. Their incredible mass meant they burned their nuclear fuel with a ferocious intensity. They lived lives of spectacular violence, shining with a brilliance millions of times greater than our sun, only to explode in supernova after just a few million years. That is a cosmic blink of an eye. This is precisely why they are so elusive. No telescope has ever directly seen a population 3 star. They vanished long ago. So how can we possibly know anything about them? Astronomers have become cosmic forensic scientists. They use the most powerful supercomputers to simulate the conditions of the infant universe, watching as virtual clouds of gas collapse to form these first stellar giants. They also search for chemical fingerprints. When those first stars exploded, they scattered the first heavy elements they had forged in their cores across the cosmos. By studying the composition of the oldest stars we can see, which formed from the ashes of those first explosions, we can work backwards to understand their parents. One of the most intriguing debates is whether these colossal stars could have had planets. With no heavy elements to form rocks or metals, any circling bodies would have been utterly alien, likely just vast spheres of gas. And their supernova deaths were not an end but a crucial beginning. Those cataclysmic explosions were the universe's first forges, the very events that seeded space with the carbon, oxygen, and iron that would one day form planets, oceans, and life itself. We are literally made from the stardust they created. The death of those first stellar titans was not the end of darkness, but the beginning of a new cosmic day. Our next great mystery asks a profound question. When exactly did the lights first turn on? This pivotal moment in cosmic history has a name: the Cosmic Dawn. It marks the end of the universe's dark ages and the birth of the very first luminous objects. Pinpointing this exact epoch, however, is one of the most difficult challenges in all of astronomy. The light from those first stars and galaxies has been traveling for so long, over 13 billion years, that the expansion of the universe has stretched it enormously. This stretching effect, called redshift, transforms the original visible light into incredibly faint infrared signals. It is like trying to hear a whisper from across a vast and noisy canyon. This is precisely why the James Webb Space Telescope was built. Its powerful infrared eyes are designed to hunt for these ancient whispers, to stare back in time further than any telescope before it. Current estimates suggest that the cosmic dawn began a few 100 million years after the Big Bang. That may sound like a long time, but on the cosmic scale, it is a remarkably swift transition from total darkness to first light. Yet this timeline is not written in stone. It is a moving target. Every new deep field image from Webb, every faint smudge of light that could be a primordial galaxy, has the potential to push this date back even further or reveal that stars formed earlier than anyone predicted. The quest to find the exact moment our universe woke up is a live investigation, a thrilling race against the limits of our own technology to witness the very first sunrise. Yet that first sunrise was not a single event but a slow, arduous birth. The formation of the very first star is a puzzle that challenges our understanding of physics. Today, new stars are born within vast, dusty clouds, where tiny grains of dust and ice act as seeds, helping gas to clump together and cool down efficiently. But the first star had no such help. It formed in a universe that was pristine, composed only of hydrogen and helium gas. There was no dust, no heavy elements, no pre-existing structures of any kind. How could a star possibly ignite in such a featureless void? The answer lies with gravity, working alone in an epic, slow-motion struggle. In those primordial clouds, gravity had to coax the gas together through a process known as direct gas collapse. It was a far less efficient mechanism than we see today. Without dust to help it cool, the hydrogen gas could only shed its heat by emitting a faint, specific type of light. This made the collapse a tremendously slow and gradual process, perhaps taking 100 million years or more for a single cloud to finally condense and ignite. This leads to another open question. Did this monumental event happen in isolation, giving birth to a solitary titan reigning over an empty cosmic kingdom? Or were the first stars born in small, faint clusters, multiple beacons flickering on in the same dark nursery? Current simulations suggest that the first protostellar clouds were so massive that they could have fragmented, potentially creating small groups of stars rather than just one. But we simply do not know for sure. Unlocking the secret of that very first ignition is the key to understanding how our structured universe began its journey from a smooth, dark sea of gas to a cosmos filled with light. Gravity alone was not enough to build the first stars. Something else provided a hidden framework, a cosmic skeleton upon which the first structures could form. This brings us to our fourth mystery, the crucial and invisible role of dark matter. In the early universe, ordinary matter, the hydrogen and helium gas, was spread incredibly thin. Left to its own devices, its own gravity would have struggled to pull it together against the expansive force of the universe itself. Dark matter provided the necessary anchor. Think of it as the unseen architect of the cosmos. While normal matter interacts with light and can feel pressure, dark matter is fundamentally different. It does not emit, absorb, or reflect light. It only interacts through gravity. This meant that as the universe expanded, dark matter could clump together long before ordinary matter could, forming vast, invisible structures called halos. These dark matter halos became the gravitational pits, the deep wells that trapped the primordial gas. They acted as cosmic nurseries, gathering and concentrating the hydrogen and helium until it was dense enough for gravity to finally take over and trigger collapse. Without this invisible scaffolding, the first stars might have been delayed for billions of years or perhaps never formed at all. This leads to profound, unanswered questions. What were these first halos like? Were they small and numerous or vast and rare? Their size and distribution would have directly dictated when and where the first stars could ignite. Even more fundamentally, the very nature of dark matter remains one of the greatest puzzles in physics. Was it cold, meaning its particles moved slowly, allowing it to clump into small, dense structures very early on? Or was it warm, with faster-moving particles that would have smoothed out smaller clumps, potentially delaying the formation of the very first stars? The properties of this invisible substance did not just set the stage for cosmic dawn. They wrote the entire script, determining the timeline and the very character of the first luminous structures in our universe. The invisible architecture of dark matter set the stage, but it was the final act of the first stars that truly transformed the cosmos. Their deaths were not quiet fade-outs, but explosions of such staggering violence that they defy easy comprehension. We classify these events as pair instability supernova, a name that hints at their bizarre and ultimate power. In the core of a massive population 3-star, temperatures and pressures would become so extreme that a fundamental shift occurred. The radiation that normally supported the star against its own gravity suddenly began to create pairs of electrons and their antimatter counterparts. This process, pair production, effectively robbed the core of its supporting pressure. In an instant, the delicate balance was shattered. The star's core collapsed in on itself, triggering a runaway thermonuclear explosion that did not just rip the star apart but utterly annihilated it. There was no leftover neutron star, no black hole. The entire stellar giant was vaporized, its remains scattered across the light years. This complete destruction is one of the key mysteries, as it means we cannot find their dense remnants to study today. We are left only with the chemical echoes of their final moments. These supernovae held a profound duality, acting as both cosmic destroyers and creators. In their fury, they forged the universe's first heavy elements. The intense heat and pressure of the blast fused hydrogen and helium into new, heavier atoms. For the first time, significant amounts of carbon, oxygen, and even iron were synthesized and then blasted out into the void. This was the initial pollution of a pristine universe, a seeding of the raw materials for everything to come. The great uncertainty lies in the yield of these explosions. How much iron versus oxygen did a single star produce? The answer depends on the star's exact initial mass, a detail we are still trying to pin down. This variable enrichment meant that some regions of the early universe were flooded with these new elements, while others remained almost untouched. This patchwork of chemical diversity, dictated by the explosive deaths of the first stars, set the stage for a cosmic divide, where future generations of stars and their planets would be born into vastly different environments, some rich with the building blocks of planets and life, and others destined to remain primordial and sterile. That violent seeding of heavy elements set the stage for an even grander act of cosmic construction. We now arrive at the mystery of the first protogalaxies, the primordial seeds from which all modern galaxies, including our own Milky Way, would eventually grow. How did these initial structures assemble themselves? The prevailing theory suggests that the very first tiny protogalaxies, often called mini-halos, began as singular, massive dark matter clumps. Each one may have hosted just a single, colossal population 3-star at its heart, a lone beacon shining in an immense gravitational well, but another possibility is just as compelling. Perhaps these first structures were not solitary at all, but were instead born from the chaotic mergers of multiple smaller stellar clusters, a gravitational dance that slowly built up a larger, more complex system. This is a fundamental unknown. Was the first step in galaxy formation a quiet, isolated event or a violent, collective gathering? The initial mass of these protogalaxies is another profound puzzle. Were they truly miniature, containing the mass of only a few million suns, or could they have been surprisingly substantial from the very beginning? Their stability hung in the balance. A protogalaxy's own gravity had to be strong enough to hold onto the gas heated by its first stars. If those stars were too massive and their radiation too fierce, they could have blown the entire gas reservoir away, effectively sterilizing the mini-halo and stunting its growth forever. This delicate interplay between creation and destruction was critical. The ones that succeeded began a process of accretion, slowly attracting more pristine hydrogen gas and additional dark matter from the cosmic filaments surrounding them. They grew by drawing in matter and by merging with their neighbors, a slow cosmic snowball effect that, over billions of years, would lead to the majestic spiral and elliptical galaxies we observe today. Unraveling the birth of these first tentative structures is to witness the universe taking its first, fragile steps from a formless sea of darkness toward the intricate cosmic web we now call home. These first stars did more than just illuminate the darkness. They fundamentally changed the very fabric of space. the universe was filled with a fog of neutral hydrogen gas, and the intense ultraviolet radiation blazing from those early stellar titans began to tear this fog apart. This grand-scale transformation is known as the epoch of reionization, a cosmic upheaval that serves as our seventh great mystery. For hundreds of millions of years, the universe was opaque. Neutral hydrogen atoms, each with a single proton and electron, filled all of space, absorbing the high-energy light from the first luminous objects. But as more and more stars and early galaxies ignited, their collective ultraviolet glare became a powerful cosmic floodlight. This radiation had enough energy to rip the electrons away from the hydrogen atoms, effectively ionizing them and turning the fog into a transparent, electrified plasma. The universe, for the first time, became clear and transparent to light, a state it has maintained ever since. Yet the details of this pivotal epoch are shrouded in uncertainty. What were the primary engines of this great clearing? Was it mostly the fierce radiation from short-lived massive stars, or did the voracious appetites of the first supermassive black holes, blazing as quasars, also contribute significantly? The balance between these sources is a major unknown, as it would dictate the speed and the character of this transition. Another pressing question is how this process unfolded across the cosmos. Did reionization happen smoothly and uniformly, like a rising tide of light gradually flooding the universe? Or was it a patchy and uneven process where vast bubbles of ionized plasma, each blown around a cluster of early galaxies, slowly grew and merged until they filled all of space? Current data suggests this patchy scenario is more likely, meaning for a long time the universe was a bizarre patchwork of dense neutral fog and brilliant clear voids. Pinpointing exactly how long this entire process took and when it was completed is a key goal for observatories like the James Webb Space Telescope. Understanding reionization is not just about mapping a change in the universe's state. It is about deciphering the timeline of cosmic evolution itself, revealing how the first structures collectively altered their entire environment and set the stage for everything that followed. Yet seeing these first lights directly remains one of astronomy's greatest practical challenges. The obstacles are immense. We are trying to detect objects so distant that their light has been traveling for over 13 billion years. Over such a cosmic journey, that light has grown incredibly faint, stretched and diluted by the expanding universe. This stretching, the redshift, transforms what was once brilliant visible or ultraviolet light from a massive star into a feeble infrared whisper. To make matters worse, the journey of this ancient light is partly obscured by intervening cosmic fog, the residue of later galaxies and dust. It is like trying to spot a single, dying ember from the other side of a continent through a hazy, distorting mist. This is why we need extraordinary tools, telescopes built not just to see far, but to see in a very specific way. The James Webb Space Telescope, with its gold-coated mirrors and sophisticated infrared instruments, is our most powerful time machine, specifically engineered to capture these ancient, redshifted glimmers. And the upcoming Nancy Grace Roman Space Telescope will join this hunt with a vastly wider field of view, allowing it to scan enormous swaths of the sky to find the rarest and most distant of these primordial objects. But even with these technological marvels, astronomers must employ clever strategies. One of the most effective is to use nature's own magnifying glasses, gravitational lenses. When a massive galaxy cluster lies between us and a far more distant object, its immense gravity can bend and amplify the light from behind it, acting as a cosmic telescope that brings the faint glow of the first galaxies into sharper focus. Another strategy is to look not for the stars themselves, but for their fingerprints. Astronomers search for the oldest, most metal-poor stars in our own galactic neighborhood. These stellar fossils formed from the chemically primitive gas enriched by only 1 or 2 generations of the first supernova. By dissecting their light, we can read the chemical story of those first explosions, working backwards to understand the long-vanished stars that created them. The quest for direct observation is a multi-front war fought with advanced technology, clever physics, and the relentless patience to piece together a ghostly image from the faintest of clues. That profound transformation of the early universe, the Great Reionization, may hold the key to a modern cosmic puzzle. Our telescopes reveal far fewer small satellite galaxies orbiting the Milky Way than our most sophisticated computer simulations say we should see. This is known as the missing satellite problem, a deep mystery that connects the ancient past to our present galactic neighborhood. The simulations, which accurately model the behavior of dark matter, predict that hundreds of small dark matter clumps should be swarming around our galaxy. Yet we only observe a few dozen, so where did all the others go? One compelling theory points a finger directly at the first stars and galaxies. Their intense, harsh radiation may have fundamentally altered the fate of the smallest cosmic structures. In the earliest eons, countless tiny dark matter halos did form, just as the simulations show. These halos were filled with primordial hydrogen gas, the raw material for new stars. But before they could ignite, they were bombarded by the ultraviolet light from the first luminous objects. This radiation heated the gas, making it too energetic to collapse under its own gravity. It was a cosmic form of feedback where the first lights effectively sterilized the smallest halos, preventing them from ever forming stars. Without stars, these dark matter clumps remain completely invisible to our telescopes, vast and ghostly shadows circling our galaxy. They are there according to the math, but they are dark. This leads to a profound question. Did the specific nature of the first stars determine the scale of this suppression? If the first stars were exceptionally massive and hot, their radiation would have been far more effective at shutting down star formation in the smallest halos. A universe populated by slightly cooler, smaller first stars might have allowed more of these tiny satellites to light up, potentially matching the numbers we see today. Solving this modern discrepancy requires us to look back over 13 billion years to understand the exact character of that initial cosmic dawn. The properties of the very first luminous sources may have written a fate for the smallest galaxies that we are only now beginning to decipher. The invisible remnants of those first stellar explosions may have planted the seeds for the most powerful objects in the cosmos. How did the first black holes form in the infant universe? This is not just a question about their birth, but about their shocking growth. We observe supermassive black holes at the hearts of ancient galaxies, some containing billions of times the mass of our Sun, when the universe was less than 1 billion years old. For them to become so immense so quickly, they needed a massive head start. This leads to a deep and unresolved mystery surrounding the nature of the very first black hole seeds. One compelling theory points to the final act of the most massive population, 3 stars. When a star several hundred times the mass of our Sun ends its life in a pair instability supernova, it can be completely obliterated. But what about stars that were massive, yet fell just short of that total self-destruction? A star between about 150 and 250 solar masses might have collapsed directly into a black hole without a cataclysmic supernova explosion. This would create a stellar mass black hole seed, perhaps 50 or 100 times the mass of the Sun. Yet there is a problem with this seemingly straightforward path. Growing from this stellar seed to a supermassive giant in less than 1 billion years is a tremendous challenge, pushing the limits of how fast a black hole can consume matter. This has led theorists to propose a more exotic and dramatic alternative: direct collapse. Imagine a vast, dense cloud of primordial gas in the early universe collapsing under its own gravity. Normally, such a cloud would fragment and form many stars, but under very specific conditions, if the gas cloud could avoid fragmenting and could cool in just the right way, it might collapse directly into a black hole. This would not be a stellar remnant, but a primordial giant from its very first moment, a seed black hole containing tens of thousands or even 100,000 solar masses from birth. Such a massive seed would have a much easier time growing into the supermassive behemoths we observe. The central question then becomes which path dominated the early cosmos. Was it a universe populated by countless small black hole seeds, the quiet graves of the first stars? Or was it dotted with rarer but far more massive direct collapse black holes that served as ready-made anchors for the first galaxies? The answer is written into the properties of the most distant quasars we can detect, and it holds the key to understanding how the universe built its most enigmatic and powerful structures in the blink of a cosmic eye. The very substance of the first galaxies presents its own profound riddle. What were these cosmic islands truly made of? We often picture them as simple collections of pristine hydrogen gas and brilliant new stars, but recent observations suggest a far more complex and puzzling reality. The James Webb Space Telescope has detected something unexpected in some of the most ancient galaxies we have ever seen, a faint signature of cosmic dust. This is a genuine mystery because dust grains, tiny particles of carbon and silicon, are typically forged in the atmospheres of aging stars and then blown into space by stellar winds. To find dust in galaxies that existed only a few 100 million years after the Big Bang implies that an entire generation of stars must have already lived, died, and enriched the cosmos in an astonishingly short period. This forces us to reconsider the life cycle of the very first stars. It suggests that not only did they form and explode as supernova with breathtaking speed, but that their explosive deaths were immediately followed by a second wave of stars forming from their ashes, stars that then produced this dust in their own final act. The universe, it seems, went from pristine to polluted in a cosmic instant. Beyond the surprise of early dust, the gas within these first galaxies holds another layer of mystery. Was it a uniform sea of slightly enriched hydrogen, or was it already a complex and lumpy interstellar medium? The violent, localized deaths of the first stars would have created intense but isolated pockets of heavy elements. Imagine a single supernova exploding, scattering its newly forged elements in a vast, expanding bubble. This would create regions of highly enriched gas right next to vast territories of still pristine material. This patchwork chemistry would have had dramatic consequences. Stars forming in an enriched bubble would be born with a richer composition from the start, while stars forming just outside that bubble would be almost pure hydrogen and helium. This means the second generation of stars was not a uniform population, but a diverse family with vastly different origins and destinies, all dictated by the chaotic distribution of elements from their long-vanished ancestors. The fundamental architecture of our modern universe, with its varied stars and planets, may have been written into that initial chaotic patchwork of gas. Hidden within the smooth flow of the first gas clouds was another, more subtle force. Magnetic fields are an invisible presence throughout our modern universe, guiding the birth of stars and shaping the structure of galaxies. But their origin is a profound mystery that reaches back to the very first moments. Did the cosmos begin with its own primordial magnetic field, a faint relic woven into the fabric of space-time during the Big Bang itself? If such a field existed, it would have been unimaginably weak, a ghostly whisper of force. Yet even that faint whisper could have been enough to tip the scales. As vast clouds of hydrogen began their slow collapse, a primordial field could have provided a delicate framework, introducing a slight spin or directionality to the gas, subtly guiding how it fragmented and ultimately influencing the final masses of the very first stars. This would mean that the first stellar behemoths were shaped not just by gravity and dark matter, but by a fundamental force born in the universe's first instant. The alternative is just as compelling. Perhaps the early universe was entirely devoid of magnetism, a perfectly smooth and neutral sea. In this scenario, the first magnetic fields had to be generated from scratch. The violent, turbulent motions within the first protogalaxies could have acted like a colossal dynamo, slowly amplifying any tiny, random fluctuations into a coherent field. Or, more dramatically, the first supernova may have been the true architects. Those colossal explosions would have sent unimaginable shockwaves rippling through the pristine gas, and in their wake, they could have forged the first magnetic fields, seeding the cosmos with this new, pervasive force. The challenge for astronomers is that these ancient fields are nearly impossible to detect directly. Their faint imprint might be left on the polarization of the cosmic microwave background, the ancient light from the Big Bang, but measuring such a subtle signal is at the very limit of our technology. So we are left with a fundamental chicken and egg problem. Did magnetic fields help build the first stars, or did the first stars create the magnetic fields? The answer dictates how we understand the entire ecosystem of the infant cosmos. These fields would have influenced how efficiently gas could cool and collapse, potentially slowing or accelerating the birth of new stars. They would have guided the propagation of the first cosmic rays, high-energy particles racing through space. The presence or absence of early magnetism could have been the difference between a universe that lit up quickly with brilliant stars and one that took a much slower, more gradual path. This invisible architecture may have been the quiet conductor, orchestrating the rhythm of cosmic dawn from behind the scenes. The universe's first era of stellar titans was destined to end. The very deaths of the population, 3 stars sowed the seeds for their own successors, triggering a cosmic transition that irrevocably changed star formation forever. This shift hinged on a subtle but powerful concept known as critical metallicity. In the pristine, empty cosmos, the only way for a gas cloud to cool and collapse was through the inefficient emission of light from hydrogen atoms. But when the first supernova polluted the void, they scattered tiny amounts of heavier elements like carbon and oxygen into the mix. These atoms are far more efficient at cooling gas. They can radiate heat away much more effectively, allowing a cloud to contract and fragment into smaller, denser clumps. Critical metallicity is the theoretical tipping point, the minute concentration of these heavy elements, perhaps as low as 1 part in 100,000, that makes this new mode of cooling possible. Once this threshold was crossed in a region of space, the physics of star formation was forever altered. The universe could no longer build the isolated, monstrous behemoths of old. Instead, it began to produce entire clusters of smaller, more stable stars, the kind that could live for billions of years and potentially host planetary systems. The great unresolved question is how swiftly and uniformly this transition occurred across the cosmos. Was it a rapid, universal shift, a single wave of enrichment that swept through the universe, ending the age of giants in a relatively short time? Or was it a slow, patchy process? Vast, remote pockets of pristine gas might have remained untouched by the pollution from the first supernova for millions, or even hundreds of millions of years. In these isolated cosmic backwaters, could brand new population 3 stars have continued to ignite long after the era was thought to be over? Finding evidence of such a late-forming pristine star would be a monumental discovery, a living fossil from the dawn of time. Pinpointing the exact moment and manner of this cosmic changing of the guard is essential. It marks the true beginning of the modern universe, the moment the chaotic, brilliant fires of creation gave way to the more stable, long-lasting stars that would eventually build galaxies like our own and create the elements for life. The light from the most brilliant beacons in the distant universe carries a secret message, a ghostly fingerprint of everything it has passed through. When astronomers analyze the spectrum of a quasar, a light source billions of light years away, they do not see a clean, simple line. Instead, they find a dense, intricate pattern of absorption lines known as the Lyman-alpha forest. This forest is not a collection of trees, but a complex tapestry of shadows. each one a relic from a cloud of neutral hydrogen gas that the quasar's light encountered on its epic journey to our telescopes. This bizarre and beautiful pattern is a direct fossil record of the universe's structure during its formative years. Each absorption line is a time capsule, representing a specific cloud of gas at a specific distance, and therefore from a specific moment in the past. The density of this forest, the number and depth of these lines, tells a profound story about the state of the universe. When the forest is extremely thick and opaque, it points to an era when space was still filled with the fog of neutral hydrogen before or during the epoch of reionization. As the forest becomes sparser and the lines weaker, it signals that the universe is clearing, that the fog is being burned away by the growing light of early galaxies. The ultimate mystery is using this shadow play to reconstruct the three-dimensional architecture of the early cosmos. Each line of sight to a distant quasar is like a single core sample drilled through the ancient universe. By combining thousands of these samples, astronomers can begin to map the invisible. They can trace the vast, empty voids and the dense, interconnected filaments of gas that made up the cosmic web, the very scaffolding upon which the first protogalaxies were built. This is how we study the nursery of the first galaxies without ever seeing them directly. The distribution of these hydrogen clouds reveals the gravitational influence of dark matter, showing us where matter, both seen and unseen, was beginning to clump together. Yet decoding this record is incredibly difficult. It requires untangling which shadows come from the vast, diffuse filaments of the web, and which come from the smaller, denser gas clouds that were collapsing to form individual protogalaxies. The forest is a chaotic archive, and its deepest secrets, the precise size of the first structures, the exact timeline of reionization, and the true shape of the primordial cosmic web, are still locked within its spectral trees, waiting for the right key to set them free. Those ancient whispers of light have delivered a message that has shaken the foundations of modern cosmology. The James Webb Space Telescope's deepest images have revealed galaxies in the universe's infancy that should not exist. They are too bright, too massive, and far too evolved for their age. Finding a fully formed city just a few years after a landscape was barren would be less surprising. These galaxies appear to have built up hundreds of billions of stars in the blink of a cosmic eye, a feat that seems to defy the natural pace of cosmic construction. This presents a direct challenge to our most trusted models of how the universe works. If our understanding is correct, there simply was not enough time after the Big Bang for gravity to gather so much material and forge so many stars. So what is truly going on? One possibility is that our models for star formation in the primordial universe are fundamentally incomplete. Perhaps the first stars formed with an efficiency we never thought possible, converting nearly all available gas into stars in a single explosive burst. Maybe the initial clouds of gas were far denser than our simulations predict, allowing them to collapse into stellar nurseries with breathtaking speed. Another explanation points to a cosmic illusion. Could the intense brightness of these objects be magnified by gravitational lensing? An unseen cluster of galaxies between us and these distant beacons could be acting as a natural telescope, bending and amplifying their light, making them appear brighter and larger than they truly are. Astronomers are meticulously analyzing each candidate to rule out this effect, but some of these brilliant galaxies seem to be genuinely that luminous. This leads to the most profound and unsettling possibility. Does the unexpected maturity of these first galaxies hint at a need for new physics in the early cosmos? Could there be something about dark matter or the nature of gravity itself in those first moments that allowed structure to form much more rapidly than we currently calculate? The very rules of the universe may have been different during that fleeting primordial era. This is not a settled mystery but a live and fiery debate happening in real time. Every new data release from Webb adds another piece to this puzzle. forcing scientists to re-examine their most basic assumptions about how our cosmos grew from nothing into everything. Even the most solitary giants may have had companions. The possibility that the first stars formed not in isolation, but in binary or multiple systems, presents a mystery that could rewrite the final chapters of their lives. In our modern universe, most stars are born with at least one partner, gravitationally bound in a cosmic dance. But did this same rule apply in the pristine, simplified environment of the early cosmos? The answer is far from clear. The formation of a binary system requires a collapsing cloud of gas to fragment, to split into two or more distinct cores that then evolve into separate stars. In today's star-forming regions, dust and heavy elements make this fragmentation process efficient and common. Yet in the primordial clouds composed only of hydrogen and helium, the physics was entirely different. Without efficient cooling from dust, the gas was hotter and more resistant to breaking apart. Some sophisticated computer simulations suggest that the first protostellar disks were so massive and turbulent that they could indeed have fractured, potentially creating pairs of stellar titans orbiting one another. Other models, however, show a single, dominant core greedily accreting all the surrounding gas, leaving no material for a sibling. The true fraction of the first stars that lived their lives in pairs is one of the great unknowns. This is not a trivial detail. A star's destiny is profoundly shaped by the company it keeps. In a binary system, the stellar lives become intertwined. One star can strip material from its partner, dramatically altering its mass and evolution. A star that would have died a quiet death alone might instead be pushed over the edge by its companion, exploding in a different, potentially more energetic type of supernova. This interaction could forge a different mix of heavy elements, changing the chemical signature it imprints on the next generation. The most dramatic consequence involves their final remains. If both stars in a binary pair were massive enough to collapse into black holes, they could form a binary black hole system locked in a tightening orbital embrace. Over billions of years, such a pair would lose energy through the emission of gravitational waves, ripples in space-time, eventually spiraling inward and colliding in a cataclysmic merger that shakes the very fabric of the universe. Our observatories like LIGO and Virgo have detected these ripples from black hole mergers in the more recent universe. But the very first gravitational wave events, those coming from the mergers of the first binary black holes, would be a direct echo of the first stellar relationships. Their detection would offer incontrovertible proof that the first stars were not always lonely behemoths. The silence from that era is a question in itself. Were the first stellar births a chorus of solitary voices or a complex symphony of interacting pairs? The answer determines the diversity of the universe's first explosions, its first elements, and its first whispers in the gravitational wave background. These first galaxies were not quiet islands, but roaring engines of creation and destruction. Their most powerful voices were not light, but wind. The most massive stars did not simply shine, they screamed their existence into the void, blowing off their own outer layers in torrential stellar winds. And when their short lives ended in supernova, the explosions hurled their remains outward at a significant fraction of the speed of light. These phenomena created vast, energetic outflows, powerful gusts that swept through the proto-galaxy. This was the universe's first form of large-scale communication, a brutal feedback loop between stars and their birthplaces. The central mystery is how this conversation shaped the destiny of everything that followed. In a small, fragile proto-galaxy, a single supernova's outflow could be catastrophic. It could blow the entire reservoir of star-forming gas clear out of the galaxy's shallow gravitational grasp. Imagine a fledgling fire just starting to catch, having its own fuel and oxygen violently blown away. This would effectively sterilize the proto-galaxy, shutting down star formation for millions of years until new gas could slowly be accreted from the cosmic web. This is negative feedback in its purest form, a self-limiting process where a galaxy's first generation of stars ensures there cannot be a second, at least not for a very long time. But this violent dialogue was not solely destructive. The same outflows that cleared gas could also trigger new star birth. As these colossal shockwaves plowed through the surrounding hydrogen, they compressed vast, cold sheets and filaments of gas at their leading edges. Within these compressed layers, the density could cross a critical threshold, triggering a new wave of gravitational collapse and star formation. This is positive feedback where death begets new life. One stellar explosion could, paradoxically, sow the seeds for dozens of new stars in its wake. The great uncertainty lies in the balance of this cosmic conversation. How efficient were these winds in the unique environment of the early universe? Today, the presence of dust and heavy elements makes gas clouds more resilient, helping them to radiate away energy and resist being completely blown apart. But the first protogalaxies lacked this protection. Their pristine gas, unable to cool as efficiently, might have been more vulnerable, more easily heated and expelled by the ferocious energy of their first stars. The scale of this feedback remains one of the biggest free parameters in our simulations of galaxy formation. Getting it right is essential. If the feedback was too strong, the first galaxies would have blown themselves apart repeatedly, struggling to build up any significant mass. If it was too weak, they would have converted nearly all their gas into stars in a single, frantic burst, creating galaxies far brighter and more massive than what we actually observe in the ancient universe. The faint, redshifted signals we detect from these early objects are the final outcome of this primordial shouting match, a delicate compromise between the urge to create and the power to destroy. Scattered throughout the cosmos may be the ultimate time capsules, pristine gas clouds that have never felt the touch of a star. These are not just old objects, they are perfect relics, preserving the exact chemical composition of the universe mere moments after the Big Bang. Finding one would be the astronomical equivalent of discovering a living, breathing dinosaur from the Jurassic period. These clouds are pure, composed of nothing but hydrogen and helium, exactly as they were forged in the first few minutes of cosmic history. They contain no carbon, no oxygen, no iron, no trace of the heavy elements that define our world. They are the last untouched reservoirs of the primordial universe. To search for them, astronomers use a technique we have encountered before, but with an even more refined goal. They train their telescopes on the brilliant light of distant quasars. As that light travels for billions of years to reach us, it passes through countless clouds of intergalactic gas. Most of these clouds imprint a forest of absorption lines on the quasar spectrum, lines that reveal the presence of at least some heavy elements. The hunt for a truly pristine cloud is a search for a ghost, a cloud that leaves no such metallic fingerprint. It would show only the clean, sharp absorption line of neutral hydrogen, with a complete and total absence of any other elemental signature. This search has yielded a profound and puzzling result. After scanning the light of thousands of quasars, such perfectly pristine clouds have not been found. They are either vanishingly rare or do not exist at all in the relatively nearby universe. This absence is a mystery in itself. It tells us that the pollution from the first stars was astoundingly efficient and pervasive. The supernova explosions of those first titans did not just enrich their immediate neighborhoods. Their processed material was hurled far and wide, mixing thoroughly with the cosmic web, seeding even the most remote voids with at least a few atoms of carbon and oxygen. The early universe, it seems, had no true wilderness left untouched. Even the most isolated regions were subtly contaminated by the stellar winds and explosions that swept through the cosmos. This suggests that the transition from a pristine to a polluted universe happened with breathtaking speed. The first stars did not just light up the darkness, they fundamentally and irrevocably altered the chemical identity of all space, leaving almost no corner unchanged. The ongoing search continues, pushing to ever greater distances, hoping to find a cloud so far away that it existed before this pollution front could reach it. The discovery of even one would give us a perfect laboratory, a control sample against which to measure every other chemical process in the cosmos. The serene, featureless sea of primordial gas was not as calm as it seemed. Hidden within its smooth expanse was a chaotic and vital force, turbulence. In the nurseries of modern stars, turbulence is created by the violent winds from massive stars and the shock waves of previous supernova. It acts as a counterbalance to gravity, stirring the gas and preventing it from collapsing too quickly, which helps determine the final sizes of the stars that form. But this presents a profound puzzle for the very first stars. In that pristine universe, there were no previous stars to create these disturbances. There were no stellar winds, no supernova shockwaves. The cosmos was a silent, motionless void. So where did the necessary turbulence come from? The leading suspect is gravity itself. As the first vast clouds of hydrogen began their slow motion collapse under the pull of their own mass, the process would not have been perfectly smooth. The infalling gas would have sloshed and rippled, creating internal motions and chaotic swirls. This gravitational turbulence could have been the first stir in the cosmic pot, the initial source of disorder in an otherwise placid sea. But was it the only source? Another possibility points to the invisible architecture of the cosmos. The dark matter halos that hosted these first gas clouds were not static. They were constantly growing, merging with smaller halos in a slow, gravitational dance. Each of these minor mergers would have sent ripples through the gas, shaking it and injecting significant energy, potentially stirring it into a froth of turbulent motion. This means the very process of building the cosmic web itself may have been the engine that churned the primordial gas. The presence or absence of this early turbulence was not a minor detail. It was a decisive factor in the birth of the first stars. Without turbulence to provide support, a gas cloud could have collapsed directly into a single monstrous star. But with a healthy level of turbulence, the cloud would have fragmented as it collapsed, breaking into several smaller, dense cores that could each ignite into a star. This means the level of chaos in the early gas may have directly dictated whether the first stellar nurseries produced a solitary, 100-solar mass leviathan or a small cluster of somewhat smaller, yet still immense siblings. The initial character of the universe's turbulence set the rhythm for the entire symphony of star formation that followed. Could planets have circled those first stellar titans? The idea seems to defy the fundamental rule of planet formation. We are built from rock and metal, elements forged in the hearts of stars and scattered by their deaths. The first stars, the population 3 giants, lived and died before the universe had any significant supply of these heavy elements. They were pure hydrogen and helium. How could you build a planet from that? The traditional answer is simple. You could not. Any world would need a solid core, and without silicon, iron, or carbon, no such core could exist. Yet, nature is endlessly inventive. A new, speculative possibility has emerged from advanced simulations. Around a massive first star, a swirling disk of gas and dust would normally be the birthplace of planets. But in this case, there was no dust. There was only a vast, hot disk of pristine gas. Under the immense gravitational force of such a massive star, this disk could have become unstable. It might have fragmented, not into rocky bodies, but into colossal spheres of pure hydrogen and helium. These would not be terrestrial worlds like Earth, but something entirely alien, gas giants far more massive than Jupiter, born directly from the raw material of the Big Bang itself. They would be ghostly worlds with no solid surface, storms that raged for eons, and atmospheres that were the universe in its original, untainted state. Their existence, however, would have been tragically short. When their host star exploded in a pair instability supernova, these primordial planets would have been utterly vaporized, leaving no trace behind. This leads to an even more profound possibility. Imagine the death of one first star becoming the genesis of another solar system. The supernova ejector from a single stellar giant, rich with newly forged carbon, oxygen, and iron, could flood a nearby cloud of pristine gas. This cloud would suddenly be enriched, pushed over the critical metallicity threshold in a single, catastrophic event. It could then collapse almost immediately, forming a second generation of stars. But this time, these new stars would be born with a swirling disk that contains not just gas, but also the first tiny grains of solid material, the seeds of rock and metal. Around these second-generation stars, for the first time in cosmic history, the formation of true, rocky planets would be possible. This means the very first terrestrial worlds, planets with solid surfaces and the potential for geology, could have formed within just a few 100 million years of the Big Bang. They would have orbited stars that were still nearly pristine, in a galaxy that was little more than a faint glow. The implications are staggering. If life requires a rocky planet, the stage for its emergence may have been set far earlier than we ever dreamed. The universe may have been experimenting with habitable worlds almost from the very beginning. The faint glow of the cosmic infrared background is a ghostly echo of all the first lights combined. This all-pervasive, diffuse light is not coming from any single star or galaxy you can point to, but from the unresolved glow of countless primordial objects, their individual identities blurred by time and distance into a single, faint whisper across the entire sky. Imagine trying to hear the roar of a distant city from miles away, where the sound of individual voices, cars, and sirens all blend into one constant, low hum. That is what the cosmic infrared background is, but for light. It is the collective hum of the universe's first cities of stars. The profound challenge for astronomers is to dissect this hum, to tease apart the individual instruments in this cosmic orchestra. A key question is determining who the main players were. Does the dominant signal come from the fierce, short-lived brilliance of individual population 3 stars, those first solitary titans? Or is it the more sustained, combined light of the first protogalaxies, which housed many smaller stars shining together? The answer is locked within the subtle fluctuations of this background glow, the tiny variations in its brightness from one patch of sky to another. By mapping these infinitesimal ripples with extreme precision, scientists can perform a form of cosmic statistics. They can deduce the typical brightness and the population density of those first sources, even if we can never hope to see a single one directly through a telescope. It is like studying a vast forest from so far away that you cannot make out a single tree. You cannot see the trunks or the leaves, but by analyzing the precise pattern of light and shadow the forest casts, you can estimate the average height of the trees, how closely they are packed together, and even guess at their species. This statistical portrait is our only way to census the earliest epoch of star formation. The fluctuations in the cosmic infrared background are therefore a treasure map, pointing not to a single X, but to the hidden contours of the entire era of first light, revealing the collective properties of the universe's very first generation of luminous objects. The true identity of the first stars hinges on a single, elusive distribution. We call this the initial mass function, and it asks a deceptively simple question. When the first stars were born, were they all giants, or was it a diverse family with a mix of sizes? Most sophisticated computer simulations paint a dramatic picture, a top-heavy function where the vast majority of stellar mass was locked away in behemoths hundreds of times the mass of our Sun. In this scenario, the first stellar nurseries were factories for titans, with very few, if any, smaller stars ever forming. This makes a certain intuitive sense. The pristine gas, lacking efficient cooling, would have struggled to fragment into smaller clumps, naturally leading to the birth of colossal objects. Yet, other models suggest that turbulence and other complex dynamics in the collapsing clouds could have allowed for some fragmentation, creating a wider spectrum of masses. This possibility opens a breathtaking window. If even a small number of low-mass first stars managed to form, stars with masses less than 80% of our Sun, they would still be shining today. These would be true cosmic Methuselahs, silent witnesses to the dawn of time, still burning in the halos of modern galaxies like our own. The stakes for this mystery could not be higher. The initial mass function is the master key that unlocks the entire character of the early universe. A top-heavy function means a universe ablaze with ferocious ultraviolet light, driving rapid reionization and flooding space with intense radiation. It means a high rate of cataclysmic pair instability supernova, each one a colossal forge producing and scattering heavy elements in specific, enormous quantities. The chemical fingerprint left on the second generation of stars would be unmistakable. Conversely, a more balanced mass function with a healthy population of smaller, longer-lived stars would paint a very different picture. The early cosmos would have been illuminated by a more sustained, less violent glow. The enrichment of the interstellar medium would have been a slower, more gradual process with different elemental ratios. The supernova rate would have been lower, and the feedback on the first protogalaxies would have been less extreme, potentially allowing them to hold onto their gas and grow more steadily. The entire timeline of cosmic evolution, from the clearing of the hydrogen fog to the assembly of the first galaxies, is exquisitely sensitive to this one fundamental distribution. Finding the answer is a monumental challenge, as we cannot directly census a population that vanished so long ago. Instead, astronomers search for its ghostly imprint. They analyze the chemical patterns in the most ancient stars we can find, looking for the specific elemental signatures that only a very massive star's supernova could produce. They study the integrated light of the most distant galaxies, trying to deduce the mix of stellar masses that must have been present to create the observed brightness and color. Every new observation is a vote in this cosmic election, a piece of evidence pointing toward a universe dominated by solitary titans, or one that, even from its very first moments, cherished a diversity of stellar lives. The assembly of a galaxy is not a single event, but a complex choreography of cosmic construction. We now face a profound mystery of sequence and timing. When a primordial galaxy formed, what was the precise order of operations? Did the supermassive black hole at its center ignite before the galaxy's first major wave of stars? Or did the stars come first, building a home for the black hole to grow within? And when we look at the structure of a mature galaxy like our own Milky Way, with its central bulge and sprawling disk, which piece fell into place first? The answers to these questions would reveal the fundamental blueprint for how a galaxy is built. For a long time, the prevailing theory was a story of gradual growth. First, a vast halo of dark matter would coalesce. Then, gas would flow in, collapsing to form the first stars, building up the stellar population. Only later, it was thought, would a black hole seed form at the center and slowly grow, fed by the surrounding activity. But observations from the James Webb Space Telescope are challenging this neat timeline. We are now seeing ancient galaxies that existed when the universe was less than 1 billion years old, and some of them already contain shockingly massive black holes. For these black holes to have grown so immense so quickly, they must have gotten a colossal head start. This suggests that in at least some galaxies, the central black hole was not a latecomer but a foundational pillar, forming either simultaneously with the first stars or even before the main stellar body of the galaxy was fully assembled. The formation of a galaxy's components is not a solitary process but a tense and interactive relationship. A voracious black hole, as it feeds, can unleash tremendous energy, blowing gas away and shutting down star formation across the entire galaxy. This is a form of feedback so powerful it can strangle a galaxy's growth in its infancy. Conversely, a tremendous burst of star formation can also drive powerful winds that either feed or starve the central black hole. The chronology of these events, whether the black hole activated first or the stellar baby boom happened first, would have set the entire future trajectory of the galaxy, determining its ultimate size, shape, and population of stars. The same puzzle applies to galactic anatomy. Did the central bulge, a dense swarm of stars, form first through rapid, chaotic mergers of smaller proto-galaxies? Or did the thin, rotating disk of stars settle down first, with the bulge building up later through internal processes? The order of this assembly dictates the violence of a galaxy's youth. A bulge-first scenario points to a violent early history full of collisions. A disk-first scenario suggests a more serene, gradual buildup of gas. The James Webb Space Telescope is now our most powerful time machine for watching this cosmic drama unfold. By observing galaxies at different stages of their infancy, we can arrange them into a sequence, much like flipping through a photo album of a child's growth. We can search for young galaxies that have a bright central quasar from an active black hole, but only a faint sprinkling of stars. We can find others that are brilliant with starlight but show no sign of a developed central black hole. Each one is a snapshot, a single frame in a billion-year-long movie. Piecing these snapshots together into the correct order is the great challenge. It is the only way to understand the true story of our cosmic home, from its first chaotic moments to the majestic spiral we recognize today. The fiery annihilation of a pair instability supernova was not the only possible end for a stellar titan. For the first stars, death came in a spectrum of violence, and the specific fate of each giant was a matter of its exact mass. We have already met the stars that were completely vaporized, but consider a slightly less massive behemoth, one perhaps between 150 and 250 times the mass of our Sun. In its final moments, the core of such a star would still become unimaginably hot, but it might avoid the runaway pair production that leads to total self-destruction. Instead, its core would collapse directly, abruptly, and almost silently. There would be no colossal supernova to light up the primordial darkness, no brilliant flash to signal its passing. It would simply vanish from the cosmic stage, leaving behind only a gravitational pit, a black hole born from the direct collapse of a star. This quiet death had profound consequences. A star that died this way did not contribute its newly forged heavy elements to the cosmos. Its carbon, its oxygen, all the elements it had painstakingly built in its core, were locked away forever behind the event horizon of the new black hole. This created a cosmic lottery for enrichment. One region of space might be flooded with elements from a pair instability explosion, while a neighboring region, seeded by a direct collapse black hole, would remain a chemical desert, starved for the building blocks of future planets. There was another, even more exotic path. For stars in a very specific and narrow mass range, their final years could have been a series of violent convulsions. They might have become pulsationally unstable, expanding and contracting like a cosmic heartbeat. With each powerful pulse, they would have violently ejected their outer layers into space, hurling shells of enriched gas out into the void before the core finally gave way and collapsed. This created a staggered, episodic form of pollution, a series of chemical waves washing over the surrounding gas rather than a single catastrophic blast. The challenge for modern astronomers is that we have no definitive way to distinguish between these different deaths. The stars themselves are long gone, and their chemical fingerprints can be ambiguous. How do we tell the difference between the elements scattered by a single titanic supernova and those released by a star that shed its skin in multiple pulsations before its final collapse? The answer is written into the chemical patterns of the universe's oldest stars, but the code has yet to be fully broken. Unlocking the variety of these first deaths is essential, for each end state wrote a different chapter in the early story of our cosmos, dictating where and how the seeds for future worlds were sown. The geography of the early cosmos was anything but random. To understand the first galaxies, we must pull back from individual beacons and survey the entire continent of darkness they sought to illuminate. This brings us to the mystery of their large-scale environment. Did these initial cities of stars only arise in the densest metropolitan hubs of the cosmic web, the rich intersections of dark matter filaments, or could a solitary galaxy also ignite in the equivalent of a cosmic countryside, or even a vast, empty desert void? The answer is written in their clustering, a pattern we are only beginning to decipher. If the first galaxies were highly clustered, huddled together in tight groups, it means their formation was an exclusive process, reliant on the rarest, most potent gravitational wells. Reionization in this scenario would have been a story of brilliant, isolated citadels of light, each one slowly burning a growing bubble of clarity in the neutral fog. Their collective radiation would have been fiercely concentrated, creating a universe of stark contrasts. But if galaxies could also form in more average regions, and even in the profound emptiness of voids, it paints a very different picture. A more uniform distribution would mean that the first lights were a widespread grassroots movement, a democratic flickering across the cosmos. Reionization would then have been a more even, gentle dawn, a gradual brightening from all directions at once. Current evidence from the deepest Hubble and James Webb Space Telescope fields leans towards the first, more clustered scenario. The most ancient galaxies we detect do not appear to be scattered randomly. They seem to huddle together, tracing the invisible architecture of the densest knots in the primordial cosmic web. This clustering had a direct and powerful consequence. It made reionization a fundamentally patchy process. Instead of a smooth, rising tide of light, the universe became a chaotic quilt of ionized bubbles, each one blown around a cluster of early galaxies, slowly expanding and merging until they overlapped and filled all of space. Mapping this ancient geography today is an exercise in profound extrapolation. Astronomers use deep field observations, which are like peering through a series of very narrow keyholes into the distant past. Each keyhole reveals a tiny, postage stamp-sized piece of the ancient sky, containing a few faint smudges of light. The challenge is to look at these scattered campfires in the immense dark and deduce the entire layout of the continent. Are these campfires alone, or are there countless others just outside our field of view? Supercomputer simulations become our guide, creating millions of virtual universes with different rules for galaxy formation. We then compare the virtual deep fields from these simulations to our real observations, searching for the model where the clustering of the virtual galaxies matches the pattern of the real ones. It is a cosmic matching game, and the winning simulation reveals the most likely blueprint for the universe's first large-scale structure. The stakes of this mystery are high. The initial distribution of galaxies dictated not just the pattern of reionization, but also the future of cosmic evolution. Galaxies born in dense clusters were destined for a violent life of frequent mergers and interactions, likely growing into the giant ellipticals we see today. A galaxy born in isolation in a cosmic void would have had a much quieter, more solitary existence, possibly evolving into a faint, undisturbed dwarf galaxy. The very character of the modern cosmic web was predetermined by the address of the very first lights. The invisible presence that orchestrated the first stars may not be what we think. For decades, our most successful models of the universe have relied on a concept known as cold dark matter, where the hypothetical particles are slow-moving and heavy, clumping together easily to form the small-scale scaffolding for the first protogalaxies. But what if this foundational assumption is wrong? An alternative idea, warm dark matter, proposes particles that are lighter and faster moving. This slight shift in fundamental physics would send ripples through the entire timeline of cosmic dawn. The faster motion of warm dark matter particles would smooth out the smallest clumps, acting like a cosmic iron that suppresses the formation of the tiniest dark matter halos. In a universe dominated by warm dark matter, the very first structures to form would have been larger and more massive. There would be no tiny, faint mini-halos hosting solitary stellar titans. Instead, star formation would have been delayed, waiting until gravity could assemble these larger, rarer structures. The first stars might have ignited later, and the first galaxies could have been born more mature, skipping the initial phase of tiny, fragile building blocks. This creates a direct and powerful link between the realm of the impossibly small and the vast history of the cosmos. The properties of the earliest galaxies we observe, such as their number, their brightness, and how they are clustered together, become a laboratory for particle physics. If our telescopes find that small, faint galaxies were abundant in the very early universe, that would be strong evidence for cold dark matter, which readily makes small structures. If, however, we see a scarcity of these small primordial galaxies, with lights turning on in a more coordinated, delayed fashion, it would point strongly toward the warmer alternative. The James Webb Space Telescope is now actively testing this. Every distant, faint galaxy it discovers is not just a scientific curiosity. It is a data point in a grand experiment to determine the true nature of most of the matter in the universe. The mysteries of the first stars and the fundamental identity of dark matter are not separate puzzles. They are the same story written in the fading light of the first dawn. The universe's first solid objects were not planets or asteroids, but something far more delicate: dust. The detection of dust in extremely ancient galaxies presents a serious cosmic timing problem. To build a dust grain, you need heavy elements like carbon, silicon, and iron, atoms that can only be forged inside stars. The first possible source is the violent death of a massive star. A population 3 supernova would have been a titanic forge, creating vast amounts of heavy elements and blasting them outward. In the expanding, cooling debris of such an explosion, atoms could have linked together, clustering into the first microscopic solid particles, the very first dust grains in existence. This path is incredibly fast. A single star could live and die within 3 million years, seeding space with dust almost immediately, but there is a rival theory. In our modern universe, a significant amount of dust is produced not in supernova, but in the gentle, sustained winds from aging stars known as asymptotic giant branch stars. These are sun-like stars in their final glorious phase, puffing out their outer layers rich in carbon and oxygen, which then condense into dust grains in the cold of space. The problem is time. A star like our Sun takes billions of years to reach that late stage of its life. In the early universe, just a few 100 million years after the Big Bang, there simply had not been enough time for such slow-paced stars to form, age, and produce dust. So how do we find dust where, by this logic, there should be none? This paradox forces a radical re-evaluation of the first supernova. Perhaps they were not just explosive, but were miraculously efficient dust factories. The specific conditions inside a pair instability supernova, with its unique mix of elements and rapid cooling, might have been perfect for converting a huge fraction of its stellar mass, perhaps up to half, directly into solid dust. One single star could have polluted an entire protogalaxy with trillions upon trillions of dust grains in one catastrophic event. Or the solution may lie in a previously overlooked population of stars. What if some of the very first stars were not all behemoths? If a small number of lower mass stars formed in that first generation, stars with masses similar to our Sun, they could have evolved quickly enough to become asymptotic giant branch stars and produce dust within a few 100 million years. Their contribution, combined with supernova dust, might have solved the supply problem. The origin of the first dust is not a trivial question. These tiny grains were revolutionary. They acted as cosmic refrigerants. By radiating heat away far more efficiently than gas, dust allowed giant molecular clouds to cool and collapse into new generations of stars much more easily. They shielded the earliest stellar nurseries from harsh radiation, allowing fragile chemical processes to begin. And most fundamentally, these specks of carbon and silicate were the absolute first step toward everything solid, the primordial seeds for every rock, every planet, and every world that would ever exist. We are here because, against all odds, the universe learned to make dust almost as soon as it learned to make light. The hunt for these ancient survivors is a search for cosmic ghosts. We know the colossal population 3 stars burned out eons ago, but what if smaller, more stable stars were born alongside them? If the initial mass function allowed for stars with less than 80% of our sun's mass to form in that first generation, they would still be shining today. Their lifetimes would exceed the current age of the universe, turning them into living relics from the dawn of time. Astronomers call these hypothetical objects population 3.2 stars. They would be almost perfectly pristine, composed of 99.9% hydrogen and helium, with only the faintest possible trace of any heavier elements. Finding one would be like discovering a perfectly preserved fossil from the day life began on Earth, but for the entire cosmos. The search focuses on the halo of our own Milky Way galaxy, a vast, sparse sphere of old stars and globular clusters that surrounds the main galactic disk. This region is the cosmic equivalent of an archaeological dig site, where the oldest stars in the galaxy have settled. Astronomers use massive spectroscopic surveys to scan millions of stars, looking for that 1 in a billion signature. They are searching for a star with a spectrum so clean, so devoid of the metallic lines that characterize every other known star, that it can only be a survivor from the first generation. The challenge is immense. These stars would be incredibly faint and rare, having formed in an era when such small stars were likely an extreme minority. They could be hiding in plain sight, their true nature masked by distance and their unassuming appearance. What would we learn if we found one? We could measure the precise chemical composition of the primordial universe with absolute certainty. We could test our theories about the Big Bang's nucleosynthesis with a pure sample, uncontaminated by later stellar generations. We could finally know the true initial mass function of the first stars, confirming whether the cosmos built a diversity of sizes from the very beginning. This search represents one of the most profound quests in modern astronomy, a direct hunt for a piece of the universe's original substance, a relic that holds the unaltered story of our absolute origins. The brief, violent lives of the first stars set in motion a chemical destiny that would culminate in us. Their supernova were more than just spectacular finales. They were the universe's first and most crucial distribution centers for the raw materials of life. Carbon, the backbone of every organic molecule, oxygen for water and air, nitrogen for amino acids, all were forged in those stellar furnaces and then blasted into the void. The profound mystery is whether this seeding process was perfectly tuned or merely a chaotic, haphazard beginning. The specific elemental yields from those first explosions were not uniform. A star of 200 solar masses would have produced a different mix of elements compared to a star of 150 solar masses. One might have been a prolific carbon factory, while another churned out excess oxygen. This meant that the very first planets to form in the second generation of stars were born into environments with wildly different chemical abundances. Some nascent worlds may have been bathed in carbon-rich dust, becoming soot-covered spheres where life's chemistry could have taken a radically different path. Others might have formed in oxygen-dominated systems, with geology and atmospheres we can scarcely imagine. The efficiency of this initial pollution determined the entire starting point for planetary chemistry. If the first supernova underproduced a key element like phosphorus, a crucial component of DNA and energy transfer in cells, then entire regions of the early universe could have been biologically stunted from the start. Conversely, if certain elements were overabundant, they could have been toxic to the delicate reactions that lead to life. the existence of our own world, perfectly balanced with the elements necessary for our biology, suggests that somewhere in that chaotic early distribution, a golden ratio was achieved. The iron in our blood, the calcium in our bones, the oxygen we breathe, all were once the hidden contents of a star that died before the Earth even existed. Their brief lives were the most important cosmic legacy for our own, a direct and unbroken chain from the first light to the first breath. The greatest mystery of the first stars may be the one we have not yet learned to ask. Every time we build a more powerful telescope, every time we stare deeper into the cosmos, we find something that shatters our expectations. The early universe is not a simple puzzle with missing pieces. It is a frontier where the fundamental rules we rely on might be stretched to their breaking point. For every mystery we have explored, from the nature of dark matter to the shocking maturity of the first galaxies, there are countless questions that remain entirely beyond our current imagination. We are like people in a dark room holding a single candle. We can see a little, enough to know the room is vast, but we cannot even guess at the objects hidden in the shadows just beyond our flickering light. The James Webb Space Telescope, for all its power, is not giving us the final answers. It is handing us a brighter candle, revealing just how much more darkness there is to explore. The true nature of the first stellar titans, the exact sequence of cosmic dawn, the origin of magnetic fields, all of these are profound puzzles. Yet the ultimate revelation is that our current physics, the very language we use to describe reality, might be insufficient to describe the universe in its first fleeting moments. This is not a failure, but an invitation. It is a call to a humility that is filled with pure excitement. The greatest discoveries about the first stars and galaxies are not behind us in the history books. They are still ahead, waiting in the deep, redshifted darkness for our tools and our minds to finally catch up. The final chapter of this origin story has not yet been written. From the ignition of a single star in a void of pure hydrogen to the vast cosmic web we observe today, these 30 mysteries chart the universe's most profound transformation. We have traced the journey from invisible dark matter scaffolding to the first violent supernova, from the clearing of the primordial fog to the assembly of the first galactic seeds. Each puzzle we have explored, from the shocking maturity of ancient galaxies to the ghostly presence of dark matter, is a piece of a grand, interconnected origin story. Solving them is not the work of a lone genius, but a collective human endeavor, a global collaboration powered by relentless curiosity and technology that pushes the very limits of imagination. The James Webb Space Telescope and its successors are our time machines, bringing us closer than ever to witnessing cosmic dawn. This story belongs to all of us. Stay curious, follow each new discovery, each faint glimmer from the edge of time, and the next time you stand beneath a dark, star-filled sky, remember this. You are not just looking at distant points of light. You are seeing the magnificent billion-year legacy of those first mysterious cosmic pioneers whose brief and brilliant lives made our own existence possible.